final part of this lesson of analyzing rational functions and graphing rational functions is the location of holes. To find the location of holes, it's always the best practice, I still feel, is getting your equation written in factored form. So first thing I'm going to do is I'm going to write g of x in factored form. So it'll be an x plus 4 times an x plus 6. The denominator will factor into an x plus 4 and an x minus 3. Okay, so this is the original equation. We want to pay attention to it because it's going to help us state its domain, and it'll also help us find the location of holes, vertical asymptotes, and also our x-intercepts. We know that we have a removable discontinuity, or a hole at x equals -4. That's going to be part of your domain, so let's take care of that domain right away. What are the values, input values, that the original function cannot obtain because it will be undefined? So in set builder notation, x is going to be an element of real numbers. There are two numbers that I know the x values cannot be, such that do not let x equal a -4 and do not let x equal a +3. The location of any holes or any vertical asymptotes must be restricted in your domain. So this will always be a combination of vertical asymptotes plus whatever you have for any holes in your graph. So our two inputs that will create a vertical asymptote or a hole are -4 and 3. So the domain is taken care of. Determine any vertical asymptotes. So in this problem, we have a vertical asymptote of x equals 3. We also have the location of a hole, so I'm going to take care of that one right away because these kind of go hand in hand. There's going to be a hole at x equals a -4. So we could reduce this equation now and look at it as g of x equals x plus 6 all over x minus 3. And we can kind of use this for the rest of the evaluation of our function. We got the location of the hole in the vertical asymptote, that's important. But now we can go ahead and get the other components of our graph. The other components we'd like to find is location of any horizontal asymptote. So we'll look at a matter of degree. It's a second-degree polynomial over a second-degree polynomial, so there's a tie. When there's a tie in those, we look at the leading coefficients, and we're going to say y equals the ratio of leading coefficient of 1 over 1. So the horizontal asymptote is just nothing more than 1. So now we have vertical asymptotes, horizontal asymptote, hole. Next thing we're going to go find are the x and the y-intercept. So the x-intercept. In order to find the location of your x-intercept, you want to make sure that you have the output equal to 0. So what we can do is, this is where I'm going to use that reduced equation. Rather than using the original, I'm going to use the one that has the removable discontinuity. And to find the x-intercept, what we want to do is we want to force the output, the g at x, to equal 0. And now we have x plus 6 all over x minus 3. Just to keep reviewing this concept, the only way a fraction can equal 0 is if the numerator is equal to 0. So all we do is we look for the x-intercept, is what is the 0 associated with the factors of the numerator, and that is when x is equal to a -6. The y-intercept, in order to get the y-intercept, what we do is we put in zeros for x. So if we put in zeros for x into our equation, we put in a 0 for x here, and we put in 0 for x there, we have a +6 divided by a -3, or our y-intercept is at a -2. So we got most of the critical features of our graph, and now we can go ahead and do a little sketching of this graph. So again, x-axis, and y-axis. Okay, so let's put in our vertical asymptote of x equals 3. So we've got 1, 2, 3 units. We'll get our vertical asymptote located. Stretch that down a little bit. So that's at a +3. Next thing, we have to have a hole of -4. So what I do with that hole is I marked it off. 1, 2, 3, 4. -4. I don't do anything with that for a little bit, but I know there's going to be a hole there. So I got to keep that in mind in my graph. Next thing I want to plot is the horizontal asymptote, and I've been using that pink. We want to put that at a +1. I have to slide that down a little bit. We'll use that as a mark of 1. So this is at 1. This is a 1. This is a -1. Our scale is 1. Next thing we want to plot is our y-intercept of a -6. So if that's a -4 out there, we'll go 2 more tick marks, -5, and just extend this line a skosh, and then we'll have it, -6. So it's got to cross the x-axis at -6. The y-intercept's at a -2, so go down 1, 2, and our graph has to cross at a -2. Okay, so we got all of our main components in our graph. Now we got to look at sketching our graph. Again, as I look on the left side, I'm very suspicious we're getting the x-intercept here, we're getting the y-intercept there, and then we got a vertical asymptote. My guess would be as we're coming along here, I'll stretch out this horizontal asymptote as well. We've got to be approaching the horizontal asymptote. We're working down through our, that's not a very good path though. Approaching our horizontal asymptote. As x goes to -infinity, we've got a couple of marks to hit. One is coming through our x-intercept, the other one is coming through our y-intercept, and it's coming down towards our vertical asymptote. That could be one path. Then if it's on a -infinity on the left side, it's probably coming from a positive infinity on the right side. And this is where we do that sign analysis just to confirm what we have. We can use our reduced equation of x plus 6 all over x minus 3. And I'm just going to choose a number close to 3, so I'm going to use something like 4 would be a good one to use. So if I do 4 plus 6, that's going to be positive. 4 minus 3, that's going to be positive. And positive divided by positive is a positive, so it's coming from positive infinity. So as I kind of expected, it's coming from positive infinity, coming down and working towards your horizontal asymptote. The only thing I didn't like about the path that I drew here, it probably will not dip down. It's just a matter of my scaling not being quite as accurate as it should be. It probably has a nice smooth path through here through the -2. But again, because of my scaling, it's probably getting that little bit of a dip in there. So it's got that butterfly graph look. That's what we're looking for. And this one has a hole in it, so the next thing I want to do is I want to go find that location of the hole. That's where I mark that -4 out. I know that wherever that graph is, at a -4, there has to be a hole in it. Now, this year in the textbook, what they're asked to do is find the location of that hole. So if we put a -4 into the equation, we can see what that value would be. So what we're going to do is we're going to calculate g at a -4. We're supposed to find a hole there, and what would the output have been? We used our reduced equation, x plus 6 over x minus 3. So we're going to put in a -4 plus 6 all over a -4 minus 3. And that's going to give us a positive 2 over a -7. So our y value should be at a -2/7. And that's where this should have been a little bit tighter up here, and that's why I'm getting that weird bowing in this graph. So try this one more time. This was -1, 2, 3, -4, and this was at a -1, and then we had a crossing at a -2. Okay, getting closer. Now at a -4, we have to have a hole at -2/7 is what we found. So if this is 1, -2/7 is just slightly above that, and then -5, -6, it's got to cross through here. So these are pretty tight in here, and they're heading down towards this -2, and then it's got to head down towards that vertical asymptote. And this one's got to head towards the horizontal asymptote. And that's a little better shape, and I think I got it squared away with that hole. So now put a hole in your graph. Remember, it's not defined there, and now our graph is complete. We'll look at a second example of this. Get some workspace here now. And we'll see how much more room we need. First thing we're going to do is take each of these and write them in factored form. So for c of x, the factors of 3 that we need are going to be x minus 3 times x plus 1 all over. And the denominator, we're going to need factors of x minus 5 and x plus 1. So we can quickly see that we have a hole here at x minus 1. We have common factors. So we can remove that discontinuity. So we'll start looking at our domain and picking off all the information that they asked us to find. Domain. Domain can't be anything that creates a denominator of 0, which means we just find the associated zeros of the denominator. That means we need the set of x, which is an element of real numbers, such that x cannot equal 5 or -1. Next thing we want is the location of the vertical asymptote. The only vertical asymptote we have is where our associated 0 is equal to x minus 5, and that means we have an x-intercept, a vertical asymptote at x equals 5. We also have the location of a hole in this graph. So we have a hole at our location of our associated 0 with our common factors, so that means when x equals a -1. The next thing we can look at is the location of any horizontal asymptote. So the horizontal asymptotes, it's a second degree over second degree, which means it's going to be the ratio of the leading coefficients, which again is 1 over 1, or just 1. So we have vertical, horizontal, holes. Now I need x and y-intercept. So x-intercept. The x-intercept is where the numerator is equal to 0. We remove the x plus 1s from our equation, so they're no longer there. So really I can just think of an x minus 3 all over an x minus 5, our simplified version of our equation. The only way that we can get an x-intercept is when the numerator is equal to 0, so that is when x is equal to a 3. The next thing is the location of the y-intercept. The y-intercept is going to be when we put in zeros in for x, and then we're going to figure out what our y value is. So in this one, we're going to find y when we put in zeros for x. That's going to be a -3 over -5, or basically it's going to be a positive 3/5. So our y-intercept is a positive 3/5. We should have enough information now for us to graph. So I have the x and the y axis still here. We need a horizontal at 1 again. We need a vertical asymptote at 5, so we'll try to sketch that one out. 1, 2, 3, 4, 5. Place the vertical asymptote at 5. So I keep track of the numbers? That's at a 5, that's at a 1. We have a hole at a -1, so again, right away I want to keep that in mind, so I want to make sure I put a hole here at -1 when I get finished with my graph. What else we need? Y-intercept. X-intercept at positive 3, so we're going to cross here at a positive 3. The y-intercept is at a positive 5/3, so if this is 1, positive 5/3 is just a little bit more than a half, so it's right in here. And that's all of our critical information that we have to put on there. Vertical, hole, okay. So now what we're going to do is a sign test on this. So all I want to do is grab a number that is close to 5, which is a 6. I already kind of know that because it's crossing here at the x-axis and crossing here at the y-axis, it's probably approaching from the horizontal asymptote, coming through your y-intercept, coming through your x-intercept, and then coming down towards your vertical asymptote. If it's negative on the left side, then it's going to be positive on the right side, so it's going to be coming down from positive infinity and then heading towards your horizontal asymptote to the right. But I can always do this sign test, sign analysis test, to make sure that we are at a positive infinity. So I take that reduced equation, x minus 3 all over x minus 5, and I test it with a 6. If I put in a 6, 6 minus 3 is going to be a positive number, 6 minus 5 is going to be a positive number, and I'm just reaffirming that, yeah, it was coming from a positive infinity. So on the other side, it should be coming from negative infinity, and that matches well with hitting our x-intercept and our y-intercept. So that should be all the components that you need to do in order to graph rational equations. There's quite a bit of information in there. Like I said, hopefully you've retained some information from last year, but now we've got the holes, the vertical asymptotes, the horizontal asymptotes, the location of any oblique asymptotes, and we've also restricted the domain range. So that's what we're working on for today, getting the graphs of each of these functions. So if we have questions, we can entertain those tomorrow in class.